let's get started.
All right, hello everyone. So welcome to today's UMD Quantum Matter Journal Club. Today we're glad to have the old friend Yuxuan to give us a talk on the twisted quantum double. So Yuxuan is currently a student with the Professor Mason Barkersley in lots of things like topological quantum matter, etc. So welcome, Yuxuan. You can take it over.
Hello, everyone. Actually, before this talk, I claimed that I'm going to talk about twisted quantum double and with diagram Witten theory, some relations. But now, I'm not exactly sure if I have the time to discuss them both. I will just start with the quantum double and discuss some implications on like how it defines the anion type of your model. And if time allows, I will talk about something more. How?
Right arrow.
It doesn't work. Oh, fine. Okay. So let me introduce you to some background. So why do we care about this quantum double? So this model is first publicized by Kitaev. I wouldn't say Kitaev proposed this model. Like I will explain it later. But Kitaev has a paper on this. And the intuition is that he wants to generalize the T2 toric code for a general group G, where G is a finite, maybe non-abelian group, but it cannot be an infinite group. So you cannot have a U1. But I believe some mathematicians are trying to expand that to a compact Lie group, but I'm not sure what is the exact process. So eventually I will tell you, given a definition of the group G, you can get the information on anion types and their fusion gradient statistics. And some application for this is that it can construct a stabilizer code. I will refer you to this archive paper that is published very recently, I believe 2022, and Arpit just recently gave a talk on this. On some related stuff, but it is a fun application. But that is not what I'm gonna talk about. So I will be mainly talking about some mathematical implications, but let's now first construct the model. Okay, so let's remind you that since this is an extension to T2 toric code, I first expect that you know what T2 toric code is. So a T2 toric code is defined on a square lattice. Let's actually switch. Can you switch to the whiteboard?
Yeah, I think we can stop sharing for now. But then we cannot see anything.
I think
if
they maximize the window. Also the problem is the other people watch on YouTube, not by the Zoom.
Can you see?
It's still on.
Oh, it's a long delay, I believe.
Yeah. Let me.
Yeah, but you can see the board.
Is it clear?
Yeah, it's pretty good.
Okay. So yeah, you can start from the. You can start there.
So a T2 toric code has some Hilbert space defined on the link, or Dumpstead, and they have such a commuting projector Hamiltonian.
Maybe louder.
Where each one of the operator, which is for example AS, is defined as for example on this side is defined as the multiplication for the 4 sigma x operator around a vertex, and the BP operator is defined as some multiplication for some sigma c operator around the plaquette. So you can actually prove that all of the operators, no matter whether they are adjacent to each other or not, they commute with each other. And so this is a commuting projector Hamiltonian, and the ground state is the weighted average of all the closed loop configurations. So that implies if you're on the torus, there's gonna be some non-trivial loop that is going around the torus, which give you some ground state degeneracy. Okay, let's get back to the quantum double.
Yeah, we can share.
By the way, you can feel free to pause me if you have any questions.
I think we will. Yeah, we'll just use this just to.
Okay, so
It's
so what is a
easier.
generalization?
Oh, sorry. Let me share it.
So Coulomb double basically generalizes in two ways. First is that it is no longer defined on the square lattice. It can be an arbitrary lattice, where you can have like basically anything as long as it's planar. It's being 2D. And now the Hilbert space on each link is defined with label G for some group G. And since this group G has an inverse, we can, when we draw this graph, we have a direction for the arrow. And if we want to draw this graph reversing the arrow, then we need to like reverse the label of that group G to G inverse.
But why is it like equal to, or is just the notation? Is it a typo?
No, it's just how we define how we can draw this graph.
Why G is equal to?
No, it's not.
No, it's not. G goes, sorry. That's its right arrow, I believe.
Look at the diagram.
Yeah. So it should be right arrow. You cannot.
Yeah. It should be right
So
arrow then. Yeah, I think that's the typo.
Yeah, that's a type. Okay. And we can define a similar Hamiltonian. I will not claim it's a commuter projector, but I will prove it later. So what are these AS and BP operators? To understand this AS and BP, we need to first define what is an ASG operator. So if you look at this ASG, its operation is around the vertex, and it will modify the Hilbert space in the following action. If the arrow is pointing inward to the side S, then it will multiply G inverse on the right of that G. If the arrow is pointing outward, you can multiply a G on the left hand side of that arrow. So, and the AS operator is the weighted average of all the possible AG operators. So if you have for example, G is a C2, then there are two possible gauge transformation. One is the trivial transformation where you do nothing, and the other one is being transformed as C2. So physically, you can interpret this as a gauge transformation. So why is that? Since we can interpret the group on the edge as a vector potential, and the gauge transformation basically add a gradient to some position, and this is basically you're adding a charge on the set S, which has an outward pointing G, and you upon some direction orientation action, you can define it this way. So this is AS. Now you can also define BPH, BP using BPH. So what is BPH? BPH is a diagonal matrix. It doesn't do anything on the Hilbert space, but it will give an eigenvalue of 1 if the holonomy around the plaquette, being the multiplication of all the labels. If it's H, it will give you 1. If it's not H, it will give you nothing. So and the BP operator is just defined to be the flat connection definition being H equals to 1. So this constraint that the flux through each plaquette needs to be nothing, and there is no holonomy.
So you're saying that if it is like say counterclockwise, then it is 1. Then it's not counterclockwise. Then it's
we
one,
just we have some canonical definition of the orientation.
yes.
We choose it to be counterclockwise.
Okay.
For this thing, the counterclockwise and the clockwise doesn't make any difference because it's just like both will give you no holonomy for this BPL. But for some general BPH, you do need to have a canonical direction.
And there's also a problem of the starting point, right?
Yes, there will be a problem with starting point. Yes, if it's not abelian, things will be different. But since everything, no matter if you have a abelian group or non-abelian group, if H is 1, everything is commuting with H. So that ignores the problem, but this problem will occur later. I will have some discussion on that. Thank you for pointing out. Let's discuss what is the property of these two operators. So I will claim the property is just their commuting predictor. Now I'm going to prove that. So why? First of all, why are they predictors? It is because when you're acting, so for example, when you're acting on AS for some site, then you will obtain a weighted average of all the possible gauge transformation configuration, and doing on it twice doesn't change anything. You will still have a weighted average of all the possible gauge transformation configuration. So A squared equals to AS. That's why. Yes, it's a projector by definition. Now, BP is a projector because it is diagonal, meaning that so first of all, it doesn't change the your Hilbert space, and it will give you eigenvalue 1 if it satisfies some conditions. Otherwise, it will give you 0, and 1 square or 0 square is just still 1, 0. So BP square is BP. And okay, let's actually discuss. So for these two, why are these two correct? It's because first of all, if they are very far away from each other, obviously they commute. And if you do that, if these S and S prime are adjacent to each other, then so you can imagine one will add some factors to the left of the link. One will add some factors to the right of the link because okay, let's actually draw this. Assuming there's a, I hope you can see me. S prime. So acting on. Okay. Acting on AS prime. So obviously, this action on these links wouldn't change if I permute the operation. But what about this operation? What about this link? So let's say before it is G, then after AS, it is some weighted average 1 over G. Let's define the direction to be this way. If it's outward, I believe it is you act some G on the left, Gi sum over I. Now, in the perspective of this S, you will then add some J, 1 over G, J inverse. So you can see that no matter which operator you're acting on this link first, the ending result will be the same. So similar for BP and BP prime. They commute. Obviously, if they are very far away, they commute. And if they are close to each other, it's like whether you constrain the left placket to be 1 or constrain the right placket to be of the good holonomy will give you the same result.
I think since they are diagonal. So
yeah, they're diagonal. Yes, yes.
So they commute.
So they commute. But maybe some non-trivial example shows up for this one. So let's actually prove that. So you can see, assuming there's a placket here, So if you assume they're randomly connecting 2 to 3 with some other links, there's a plaquette here and there's a site here. So ASG acting on this will give you this. And if you calculate BP on these two links, this S2 and S3, you will get G2 inverse and G3 inverse. But if you calculate BP after acting on ASG, you will actually get the same thing because this G inverse cancels each other. So I proved that this also. So eventually,
I think there's a good graphical notation of doing the group multiplication on the link, like drawing a link to be a multiple arrows, like G1 times G2 equals just draw two links and G1 and G2.
yeah, you mean the graphical calculus?
No,
Right?
that-
I think you can do it. So
Yeah.
do you also need to inherit some?
Yeah, so there's
Yeah, go for it.
yeah, there's like, if there is a star operator and AG just means like, and then show another set of G insects.
Yes.
Like
So
that.
this is basically adding like gauge transformation, adding a chart there.
So
that
like
there's
if a plaquette is like calculating the holonomy here, it can be easily seen that it cancels.
Yes.
The red arrows will cancel each other.
Yes. But okay, but there will be some non-trivial problem if you choose your starting point BP. So if you have a BPH actually. You start with some BPH. And you add for some AG, let's write it using some cool notation, AGS. Then if you choose your starting position to be the site S, then
Yeah, there will be a
there will be, and your H is not 1.
Yeah, it will get conjugated.
So when you go around the loop, you will have some, this will give you, so BP originally have, let's call it G1, G2, G3. So G1, G2, G3. Now it is
No, there is a
G1, G1, G.
G1, G2, G3 is still in sequence, but
G
there will be
inverse, G2, G3. Oh, this is G. Yeah. So, and this will, in the case H is 1, this is just 1, so cancel each other, everything cancel out. If it's not 1, there's going to be a problem. If it's non-abelian, that is. If the group is non-abelian, there's going to be a problem. Yeah. I will get to that later. So, what is the consequence that this is a commuted projector? Is that you can write the ground state. So you can simultaneously diagonalize your Hamiltonian and every operator that you have. So the ground state is just each operator having eigenvalue +1. So your ground state wave function can be written as the weighted average of all the loop configurations that you can have. But there's a slight difference from the toric code configuration. Is that your loop can be colored by any G, not just 0 or 1 in the Z2 gauge theory. So imagine if you have a Z3 gauge theory that can be colored by 1 or 2 or 0. But otherwise, they should be the same. So, and now I'm gonna talk about.
And also something will happen when two loops intersect.
Yeah, yes. So
Yeah,
definitely, yeah. Especially if you have some non-abelian structure, then that will happen. But there will be some other discussion. But let's discuss some probably non-trivial stuff. And let's go back to such a configuration where we define the site S to be just this side and the plaquette to be here. And we now let's ignore all the S and P. to simplify the notations. And you will find the properties for each individual AG and BH operator to satisfy this condition. And if you define the generator of your algebra, DHG, to be like this, BH times AG, then it will give you some algebra. And the algebra generated by DG is called the Drinfield quantum double. DG of G does give you the name quantum double. So as I claimed before, this model is not first proposed by Kitaev, but actually by Drinfield. So if you know category theory, there's a Drinfield has a lot of contribution there. And if I
So why is it called double? It's double something.
yes, basically, okay, this is a notation thing, but I think the double is just there's a BP and H. There are two kinds of objects. That is the double. Yeah, but it turns out there's more structure to this DG, other than the algebraic structure. There's a you can define a co-algebra structure. So what is a co-algebra? As you can see here, algebra take you from 2DG to 1DG. Yes, but now if you define a co-algebra structure, this takes one AG operator to two copies of the AG operator, and one BH to two copies of BH. Why do we want to do this? Because when you have algebra structure and the co-algebra structure, you can now define a fusion category on the system. And the representation of DG will be the tensor category. I have ignored a lot of details in this argument. Actually, you can define even more structures to this. You can even define braiding structures, so that now it is a braided fusion category. But I'll ignore that. If you want more details, you should look for at the semi-triangular Hopf algebra in some, for example, in this book.
Do AG tensor, are they acting on different sides?
Yes. So I will talk about what is the implication of this in the next slide. So what is the physical interpretation for this? So originally you have one AG operator which acts on one side. Now you have this co-algebra which split it into two copies of the AG. So this physically just means if you do a gauge transformation on the combined fused particle, you also do you need to in the separate basis, you need to do gauge transformation separately on both of them. And for the BH operator, this physically means if you have a holonomy around the fused particle to be H, then you'll actually ignore some information, right? So if you do it on one of the particle and the other particle, it will have the holonomy H1 and H2, and we only constrain the total of the H1 times H2 to be H, and there's an extra degree of freedom here. So only when you define how the holonomy and gauge transformation can be fused together, can you define a fusion category here? And yes, and now I want to stress on the main results that I'm going to talk about. So I claim that although for lack of mathematical rigor, that the algebra and the co-algebra structure will give you it will give you a fusion category, and the irreducible representation of quantum double DG, this algebra DG, has one-to-one correspondence with anion types. So for example, you can the Z2 toric code is an example that it has 4 types of anions, and you can actually calculate that based on the group G, G being Z2. So let's give you an example of how to actually calculate that. But before that, let's define what actually is the irreducible representation of DG. So for now, I'm basically giving some claims without any proof. But I will direct you to maybe Mason's Mason's paper, symmetry fractionalization, if you want more details on the proof. So the irreducible representation of DG can be characterized by a pair C and chi, where C is a conjugacy class of G. Basically means if you conjugate an element within G by some other element of G, like what is the set of class that it will have? I will later give you an example. And the C is a central, like to define chi, you need to first define C. C is a centralizer of G, basically meaning that C for an element is all the group elements in G such that G commutes with this element. So maybe you know that there's a center of the group or the chiral central charge. Basically, it means what you mean by center is that it commutes with everything else. So C is a centralizer, and the chi labels all the irreducible representation of CR. So now let's give you some examples. Is there any question?
Oh, I was just asking. So for abelian groups,
Yes.
that's like C is the elements and chi is just
Okay,
the
for
units of the group itself.
yes, for abelian groups, C is just a trivially just singleton set for every element in your abelian group, because under conjugation, nothing your element will not permute to any other elements. So and C for those conjugacy, so for those elements in the singleton set of the conjugacy class, it's just a full group because it permutes with everything else and doesn't change. Yeah, basically, I just said that. But let's now discuss why we define it this way and what is the physical meaning that C and chi is. So I claim that C labels the annual flux and chi labels the annual charge. So the first argument being under gauge transformation, as I have claimed here, under gauge transformation, you will have a conjugate. The BP operator will be conjugated by G and G inverse, and BP operator basically tell you the flux through the plaquette. So C labels the flux, and chi, since charge is the dual of the flux, chi just labels the charge. We know the charge commutes with everything else inside the conjugacy class. Okay, now let's give you an example. So maybe before C3, we can give you an example on C2, C2 toric code. So we know C2 toric code has C2 toric code has 4 particles, which is E. Let's start with I, E, and E or F. Okay, you can write this in that language to be I equals to 0, 0, equals to 0, 1, and equals to 1, 0, F equals 1. And how can we see this? Because let's calculate the
Is this Z2 or Z3?
C2.
Or Z2 cross Z2?
This is okay. The group is C2,
Yeah.
but the irreducible representation is labeled by C and chi. Each
Yeah.
has a classification.
Oh,
of
okay,
C2.
okay. So here is the
What I'm writing now is all the elementary, the annual, basically, and they are labeled by C2 cross C2.
okay.
The C chi.
And this can also be described by the dream field double of Z2 is Z2 cross Z2. Is that correct?
Yeah, I mean, this is basically what I'm doing here, right? The dream field, I'm calculating the irreducible representation of the dream field double, which is the C2 cross C2 for G equals to C2. Basically, I've argued that like for a abelian group, C2 is obviously a abelian group. the conjugacy class is C2 being the singleton set for each element, and for each singlet for each conjugacy class, you can define the centralizer to be the full group, which is C2. So this is true for arbitrary abelian group. So for Z3, you will have 3 conjugacy class, and each will have the full group C3. So eventually you will have a 3 square equals to 9 annual type for Z3 abelian group. This is yes.
Like, why do we write it as coordinates? Like, can we, like, is there some meaning
As what? Sorry.
as coordinates, a pair of?
This is not
numbers?
coordinates. This is just some data that labels the annual.
So you just write it in this form. Like, does it have more meaning? Can you add 2 of them?
You mean stacks?
Is it like vectors?
Uh,
0, 0,
yes.
and 1,
So by
0,
writing this, I'm actually implying some fusion statistics, right? So I'm implying that I and E fuse to E, and or E and M fuse to M. Right? So for abelian groups, it is easy to do this by writing down these labels. It like naturally embed some fusion statistics. But for non-abelian group, this might not be so easy. Let's do an example for non-abelian group.
Do you want to share it, or do you want to do it on the whiteboard?
I will do something on the whiteboard.
Then it's hard for the online audience to see.
Okay, let's just share this slide first. Okay. So, okay. So S3 is a permutation group, which is not abelian. Let me write down the element of S3. So what S3 is S3 has the following elements. I will explain what these means later. No comma. 1, 2, 3. 1, 3, 2. So S3 is all the action you can do on the order set 1, 2, 3. Let's actually write it as ABC to avoid some confusion. ABC. So the one of this group is just doing nothing to the set, and 1, 2 is promoting A and B. 2, 3 is promoting B and 3. 1, 2, 3 is like a cyclic permutation of A, B, and C. So let's calculate the conjugacy class for this S3. I believe I done similar thing in my first presentation in symmetry independence, but let's just do it again. Okay, so what is a conjugacy class for this thing? It is obviously itself. There is only one element, because no matter how you conjugate your one in your group, you will get back to yourself. So the first conjugacy class will be just this, with the centralizer being the full group S3. You can also do it for something else. For example, you can do it for this 1, 2. And you will find that, okay, let's skip the proof. You will find that eventually they split into 3 conjugacy class, C1, C2. So it's convenient since I already draw it in this way. And the centralizer for these conjugacy classes labeled on the right. So what does this tell us? It tells us for if you have a Greenfield double for the S3 labeled for each link, then you will have 8 type of annual excitations, where this dimension, basically indicates whether your annual is abelian or not. If the dimension is 1, then you have a abelian annual. If it's not 1, then you have a non-abelian annual. Since S3 is a non-abelian group, you can expect this. Yes. Okay. What? Oh. Okay. So this is what I've discussed above is just some mathematical construction, how you can classify your annual type. But there's a more explicit construction being the ribbon operators, which is analog to the string operator, or if you're a mathematician, you call it two-hoof loop in the Z2 toric code. So why are we actually like adding these extra structures? So this figure is proposed first by Kitaev in his original paper, that he proposed these a ribbon operator that not just acting on the dual links, but also acting on the links. And this is the action. So you can actually prove that with this ribbon operator, there's only two excitations on the leftmost and on the rightmost of your operator. So if you count the flux that is picked up by this action, obviously this is y1, this is hy1. So you pick up an extra flux on this bucket, and also on the other side as well. So this is explicit construction on both sides of your string operator, some anionic excitations. And Kitaev has proved that this also gives us the fusion and braiding of any anion that you have by just, so for example, if you want a self-statistics, you can just draw 8 for your ribbon operators.
But it is not a unitary operator.
It is not a unitary.
Does it involve a projection?
What if it's not a unitary?
Because there is a projection delta G exponential 3. So
Yes.
It will send any state that does not obey that that constant to 0. So why can you say that this creates some anion? Because it's like if we really have a material that has something and we really want to create that anion, we need to do some operation which is unitary on that. So how can you say that this non-unitary string operator creates that anion? So if you really want to create some anion, you cannot just do this operator.
Okay, maybe I should go through Kitaev's proof, but I'm not sure how to think of that. Fine. Okay, let's discuss this later. I'm not sure how to prove that. So a similar construction can be seen using the paper that I claimed before. They use the twisted quantum double to construct a stabilizer code. So this is their construction on a double semion model, where they construct different kind of ribbon operators for different type of your anion string. So this is basically one direct example for doing that. If you're interested.
What is the key to the
what? Twisted quantum double. Yes. So I haven't introduced you what is a twist yet. But, so what I've introduced before are all just quantum double model without any twist. You can actually introduce some twist. So actually to introduce that twist before doing that, we need to triangulate our entire plane for some for easier computation. So we know that each plaquette has 0 flux. We can add. So if we already have a quantum double model, we can add some links such that each triangle also has 0 flux. So for example, if there's G1 and G2, you can add a link here with G1, G2, and if you calculate the flux, it will be 0.
Why do we need the triangle? Why do we need to triangulate this?
Why do we need triangulate? Because because I think it is easier to do mathematics. I think there's just mathematical reason.
Is it the reason why we want to make it like simplex
Yes, yes,
Okay,
because it's easier to calculate cocycles on simple.
okay.
Yeah.
I see.
So is the ribbon operator which you showed in last slide, is that the generalization of Wilson loop operator?
Yes.
And then if you take a loop instead of a
Yeah,
line,
then you generate nothing, basically. Yeah.
but does it measure the flux?
Oh, does it measure the flux? You have zero flux or if you are on the ground state, as I presume. So you measure nothing.
No, I think it doesn't, can you, is it the grading of, if there was an anion in between inside the.
Yeah.
Then okay. If there's an anion, yeah, definitely you can do gradings.
So if originally there is already an anion in it, then you can think of that anion as that endpoint of another string.
Yeah.
So basically doing the grading is like a crossing.
And there will be non
The
commuting.
advanced state won't get annihilated. So the state that would get annihilated is when, so what you're asking for, would be when your ribbon is cutting a point when where there's the projection that last.
This?
Right, so the projection that's removing states when your ribbon is cutting.
You mean your ribbon is exactly on
Yeah,
the anion?
So only then you'll have a problem. If not, it's
I think so.
otherwise. No, if it's in the if it's near the ground state sector. And if
This is when you construct the ribbon operator, do you just like fuse the anions that creates by the ribbon and was originally there? So basically, it's just calculate the fusion status.
no, but the delta would kill it.
Yeah, I'm not.
So you mean if there is no anion, it's near the ground state, then it is actually unitary in that.
Yeah.
So you mean there's always a constraint on?
The ground state is like a superposition of many loops. So
I'm really not sure, but Kitaev gives.
but
Go ahead.
so it's the ground state is a superposition of any kind of loops. So, but it will include some loop in which the projection is not satisfied. If it's cut. And exactly, if you use the Z2 case, the toric code case, then you will not get the X string and D string. You will get something like some kind of projection, like some linear combination of that will be the X string and D string, but originally it's not. But I don't know.
So maybe there's a sum over a lot of kind of strings.
Yeah,
So this is just the
I
label.
know that
Yeah.
actually you can do a summation to make it
OG.
unitary, but
OG.
I'm not sure like how to in a general case how is the summation done? Like if you really want a unitary operator that creates two anions from the ground state or in any state, like you want to create two more additional anion on the lattice, then how do you do, like what kind of unitary operation should you apply on the
Well,
lattice?
I think there's definitely some like FHG is definitely not the full story. There must be some addition of some sort.
Yeah, and
fix
then
it.
for non-abelian anion, I do not understand, like since there can be some non-local degree of freedom, so to move a non-abelian anion, can you always apply the same operator, same unitary on any other lattice?
Well, this is a set of operators. There's definitely going to be a different.
But like, if you really want to move that anion, rather than a term that will will not commute with something, like I give you a state which is the real physical state of a lattice, and on the lattice there are some non-abelian anions.
Okay.
Then you want to move a non-abelian
Well,
You ask me if have the operator to move a non-abelian from here to here is low. Like but if there is no other linear anywhere, it should be.
Yeah, but it still need to be unitary.
Yeah.
Yeah.
I think so.
Yeah.
So I mean, this is definitely not just the single operator that does the job. I would definitely expect something else.
Should be like sum over H.
Yeah. I think sum over G. I believe.
Sum over G, then they'll move to H in here.
Sorry. Then you can have like, arbitrary.
No, so if I sum over G, then am I moving H anyone from
Yeah.
Y1?
Yeah. Yeah. Okay. Oh, I'm not exactly sure if I have time to go through the twisted version. I will try my best. So you have the triangulation. You can define a flat bundle. A flat connection on your triangulation. And now I want to. My claim is the twisted quantum double model is just what is originally proposed by Diagram-Frieden as the Hamiltonian model of the twisted quantum double. So they're in one-to-one correspondence. So okay, let's actually look at these ASG operator again and see what exactly it does. So in the space picture, imagine you have a 2D lattice. What this ASG does is add a gauge transformation on some side S. But you can also see this in the space-time picture, where so you map this green arrow to here, and this P basically, after you evolve time, you make all the triangles inside this space-time synthesis to have flat connection, such that this constraint, the green arrow on each link to be GG1, GG2, and GG3.
This is supposed to be 3D?
Yes, this is 3D, and your original plane. So the vertical axis T.
There you go.
Yeah. So your original lattice is like this, and then after you do gauge transformation, you effectively add a link vertical to that side S, and give some extra constraint that the space-time two syntheses all have flatness.
This is a portion of the space-time. So
yes.
So actually, if you don't do the G, there are many layers like.
You have a 2D lattice. So before you mean.
But the time is evolving. So
yeah. So you can add a trivial T, right? You can add a T equals to 1 to every other.
But it's only a pyramid. But how about the other part?
That is what I'm saying. If you really want to imagine that every site is moving in T direction, you can imagine you do a trivial gauge transformation on every other side.
Oh, okay. So it's like this.
I'm not sure what you're drawing, but okay. Okay.
And also, is this space time like a Euclidean space time or Lorentzian space time?
It's Euclidean.
Yes, I think so. Actually, can you actually embed it on?
I don't know.
I think you can embed it on arbitrary closed surfaces, right?
Yeah, but if I want to think of it as a surface, then it has to be Euclidean.
No, if it's on a sphere, you can imagine the perpendicular direction of that sphere. So the T direction is out of the sphere, and the sphere is expanding in T direction. You can actually think of it is possible to do that. What?
Why is expanding
Sphere. What do you mean by Euclidean? You mean the is time direction R or S1? Is that what you're asking?
I'm basically asking.
Euclidean is like the signature.
Yeah.
Like
minus
when we write out the partition function.
Yes. Yeah, we assume it's Euclidean. Yes. Sorry. Yeah, we assume it's Euclidean. I thought you were asking the space if the spaces. Okay, fine. So normally when you construct, I ignore a lot of part, but this is one construction of the Diagram-Frieden theory based on the Gaussian wave function. So you can actually write down your Gaussian wave function in this way, where this Gij is your basis, and you sum over all possible flat connections with some parameters psi I for the weighting for each of your basis state, and you average over all possible triangulations. Actually, this n is very large because there are a lot of possible triangulations. So the twist comes when you consider different triangulations. So so it is a mathematical theorem that you can change from one triangulation to the other triangulation, to any other triangulations through a finite series of Packer moves. So what is a Packer move? A Packer move is basically, there are two kinds of Packer moves. One is you have a square and some length like this, and it goes to this. Well, 1, 2, 3, 4. This is called a 2-2 Packer move. There is one other Packer move which is called which move from this lattice to this lattice. This is called a 1-3 Packer move. So I'm not going to prove this, but you can go from any triangulation to any other triangulation using only these two actions. And so what does this action look like in the space-time picture? You can think of it in this way. So before you have some this. Before we have some triangle at time t equals to 0. Equals to 0. The 1-3 Packer move basically and if you look from top to bottom, you'll see that there's suddenly extra 3 links.
So the ground state is a state in a space, right?
Yes.
So why do you
So
sum over all triangulation?
maybe you can okay. I sum over all triangulation in the space, not in the space time.
Yeah, but in the original common double model, the system is like on the physical lattice, but
Yes.
you sum over triangulation, so it's not really on the physical lattice. It's
No,
on the
triangulations on
superposition.
the okay.
All triangulation is superposition of all kinds of physical lattices.
Yeah. So the triangulation is always done in the 2D plane, in the 2D lattice. So what I'm saying is this Packer move, we can interpret this action of Packer move as an extra lattice, an extra axis, being the time axis. And after this interpretation, these two Packer moves actually is the same thing in the following sense. So this 1-3 Packer move will create a 3 simplex in the space-time picture. And this 2-2 Packer move, if you draw that, so this is your original lattice t equals to 0. And now you're adding this one. But if you look closely, you'll find that this is also 3 simplex in the space-time picture. So in the 3 space-time picture, actually these two things, that's the same thing, absolutely the same thing. And we define the twisting to be what is the phase picked up by doing this retriangulation. So in the quantum double model, we define this twisting to be 1. So there's no twisting by doing retriangulation. But in the twisted quantum double model, we twist, we have an extra phase, extra U1 phase in the 3 co-cycle nu 3 GHK. Where so for the 2-2 Packer move, GHK is GHK. Actually draw the arrow direction.
So why do you say that quantum double model the phase is 1? Because in the quantum double model you didn't consider sum over all triangulation.
This, or maybe we can say this is how we like in the quantum double model we haven't defined the ground state in this way, right? So we can actually define using this language sum over all triangulation.
I'm confused.
Yes.
I you giving the wave function for one lattice or wave function of, so the wave function is on one particular lattice, right?
Yes, so I'm writing, okay, so what I'm writing is how this space will change upon retriangulation. Right?
I have the same question. Asking like what is the Hilbert space of the
Right.
yeah?
Is
Because you
the-
start over all triangulation, so what is the Hilbert space? Because each triangulation will give a Hilbert space.
Yes, so it's a very large Hilbert space. Different triangulations.
Is the sum for triangulations of space-time or just for triangulations of space?
Triangulation of space. Okay.
I think like it's a direct sum of all possible. The Hilbert space is a
Space
direct-
time, the space time is even larger. You can have arbitrary set. You can have different possible actions on the space time that like eventually yields the same triangulation. But you can have different set of actions.
But the wave function is for one time space.
Yeah, wave function is on one time. Yes, but you can see. Okay, okay.
And
I
one
understand
time
the
space,
confusion.
the why should I retriangulate again? It's just one fixed lattice for that.
Why should you retriangulate?
Like,
So are you asking why should we average over all triangulation?
like I'm saying, if I fix time to be something, then
Yes.
at that time I have some triangulation, which is just.
Yes, but the triangulation is not the physical. Okay, I see a lot of people misinterpret the physical lattice and the triangulation. They're not the same thing. You can have a physical lattice that is the same, but have very different triangulations. Like have arbitrary triangulations even. As long as it's plain.
1-3 Packner move, then
Yes.
does the lattice change or is it? Does it remain
The physical lattice never change.
But
Okay.
the number of edge changes, right?
The number of what?
Number of edge.
Yeah, the number of but the triangle. Okay, the triangulation.
But
ha-
so in the physical system, still like like the on each link we have a local Hilbert
No.
space for one in the group in the common double model case.
But not
okay.
always.
Okay, so yeah, maybe we are drifting away from like what is physical.
Yeah, so what is the Hilbert space here? What is the you said GIJ set GIJ, so it's still like some group element live on.
Yes, the group label is the same.
So if I triangulate, what happens to psi of G? So if I retriangulate,
If I retriangulate, okay, so for two particle, this phase can actually change from like because you have a different triangulation. This phase can actually change by this this 3 cosine. Right? So this line here is basically telling you what this phase will change upon doing retriangulation. Yeah. Let me just move on. I'm way over time. And your cocycle need to satisfy some consistency condition. This is a third cocycle condition. Why it doesn't need to satisfy this condition? So you can imagine you start with a pentagon and you iteratively do some. Okay, let's just use this. Imagine you have some pentagon and you iteratively do this 2-2 pattern move. This will changing the edge, retriangulate and change the edge. But there are 2 ways you can move from this kind of lattice to this kind of lattice. So these 2 need to be consistent. And for each Parker move, you gain an extra phase, you gain an extra neutral. So, but eventually these 2 paths, since these 2 paths give the same triangulation, you need to expect that the top path and the bottom path will give you the same neutral. So this is basically the cocycle equation written here.
So is this the only constraint which comes up?
Yes, I believe so. This is the only constraint. So, okay, now I'm claiming that the digraph-Witten theory actually is just the Hamiltonian picture of the twisted quantum double. Yeah. So I remind you that the Hamiltonian that we originally have is this commutative vector with AS and BP defined in this way. But now, in this twisted cone double, the AST picture needs to be changed because after this gauge transformation, in the space-time picture, we're creating 3 more 3 simplices, and each simplicity, each 3 simplices will give you a new 3 cycle. And this is on the bottom because it's in the reverse orientation. So yes, this will give you the diagram weight and Hamilton. Okay. Thank you for your time on this. That's all my talk. Okay, any questions?
I still do not understand the Hilbert space.
I mean, I think somewhere here I made some mathematical transition. We're
But in the final Hamiltonian, actually, the only modification is the A term, like.
You can do an example. Like some
I think, as far as I know, the Hamiltonian is still on the finite size lattice, but on the finite, like on a single lattice, not on the.
yes, it seems the dimension of the Hilbert space has changed. Quite weird.
When you retriangulate, what happens? The retriangulation change the degrees of freedom on the plane.
I feel like the triangulation has nothing to do with the plan.
But it can only be like cutting a square in half, that they will not change. No.
It doesn't need to.
No, even
Assuming you
that
have a
change something.
the site doesn't need to.
change the group elements on each ring. But I don't know why we need to reach.
So I think the crucial question is that what is the Hilbert space? Like, is it infinite or is it finite or is it?
Finite.
Yeah, if it is finite, then how do we prove that a different triangulation will give us like the same or a different physical state?
If you sum over all the triangulation, it will not be finite because you can cut it in half and in half and so on.
Yeah,
Yeah, I remember. There need to be some color. Yes, yes.
No, but the wave function is for a fixed, like I'm given a system and I know what the lattice is and I want to give the wave function for that system. And for the Hilbert space is given beforehand. Some material that's inside some fixed.
Then you cannot do one through Parker. You're saying that you cannot add a link or change a link. You cannot do a triangulation at all.
That's what it is.
I think I still don't get the physical meaning of it. Like, I understand that we can assign some sort of
I agree. I did this very quickly, but there is an alternative picture for this from the a partition function, and that has more physical meaning. So maybe I should just start from the other one.
right.
Okay, but I guess the main topic of my talk is the quantum double and the implication on any size. Yeah, so I'm not sure when I do these slides, I'm not sure if I will have time to cover these. So it's kind of a bit rushed. So sorry for your like 10 minutes extension.
Right. So if there are no more questions, let's thanks Yuxuan again for today.